That was just an interpretation of this multiplicative inflation, which is essential. It has to do with the fact that we're overestimating the Kalman gain in a sense, but that's another little issue. And now, to finish off for today, at least my bit, before you do go on to the hands-on and doing parameter estimation. An active area of research is now to, can we go beyond somehow the ensemble Kalman filter? And I sort of already indicated that, there are certain options. And one that's been followed by, for example, by the group in Zurich, Künsch, and they also actually implemented that into an operational system, the Swiss operational system, is sort of a hybrid approach that allows you to adaptively bridge between an ENKF and a particle filter. And there are various ways to think about it, but you can either think of it as you take your likelihood function, it's e to the something, and you just formally introduce alpha and 1 minus alpha. So you split your likelihood into two parts. And alpha is between 0 and 1. And then you get a likelihood 1 and a likelihood 2. Now having this alpha there basically means that you sort of split the measurement error. You can also think it this way. So you change the R and you make it slightly larger. And so basically you now can take the data twice, but with an increased measurement error. So that statistically after you've done it twice you get back to the same result. But now you can use different techniques for each of these two things. So you can say, well, for the first component I have a change in measure corresponding to this part of the information, and then I follow it with a second change of measures corresponding to the second part of the information, and it sums up to the correct thing. I guess that's also a little bit behind running in place, this kind of splitting, that you use the data several times, but here you actually don't overdo it in a way. You don't, I mean, statistically it's still correct. And as an end result, you get the right, you just split it into two steps. One step, you split it into two steps, and you can split it into more steps if you like. And then let's say you apply a particle filter for the first thing and the ENKF to the second, and then you can bridge by choosing alpha equal to 0, then the particle filter would disappear and the ENKF takes over, or you take alpha equal to 1, then it's the other way around. And then the question is it better to first use the particle filter on the ENKF? I mean, we personally found that using the particle filter first helps. It's better than doing it the other way around. The intuition behind that is that your uncertainty might be initially more non-Gaussian, but as you use information, things contract down to Gaussian again. And so the last bit you can do Gaussian, so rather than going the other way around. And as I said, the group on the ETH, Künsch, they effectively actually did it the other way around. And they have another interesting interpretation, which you can also, is another thing, very natural thing to bridge these filters, a particle filter with an ENKF. The ENKF uses a single Gaussian. The particle filter instead uses Dirac deltas. So what is something that is a compromise between these two things? Well, a Gaussian mixture. So you make the Dirac deltas, which I introduced in the beginning as a collapse of a Gaussian. Now you actually go back to a certain variance. And now you have a sum of Gaussians. And what you want to do, in addition, you slightly shift these Gaussians. So you not just center them about where the particles or your ensemble is sitting, but you shift them slightly so that the mean of the ensemble under this Gaussian mixture is still the same, and the variance is also still the same. And you can do this. So basically what you need to do, you have these Gaussians, and you have to shrink them a little bit so that the overall variance still remains the same, right? And that also allows you, and then if you do this to the extreme, then all these Gaussians collapse into a single Gaussian, and you're back to the ENKF, or you just take a portion of the Gaussian, I mean the forecast covariance matrix, and then these remain separate Gaussians. But it's a very natural way of bridging a single Gaussian with a mixture of Gaussians all the way down to Dirac deltas. And you have, again, it's just a single parameter alpha, which varies between 0 and 1. And with Gaussian mixtures, in particular if the likelihood is Gaussian, then you can do everything analytic as you did it for a single Gaussian. So there's a formula you can, and basically the posterior is again a Gaussian mixture, now weighted, and each Gaussian itself is treated like with the ENKF applied to that single Gaussian. It's very simple. And so you can basically then move each particle in it's to each mixture component as an ENKF. It gets a weight, and then you have to use some techniques to get them equally weighted again, and you can use the techniques I told you about in the third lecture, like these transport algorithms, for example. And then you can naturally bridge, and you can test it, and it's simple. Now, one open problem there is how you choose the bridging parameter effectively. Now, one idea, of course, that's quite natural, and that's what we've been using in practice, is to say we basically use the weights. I mean, these are the weights that come with the Dirac deltas, but you get similar weights for the Gaussian mixture component. And if the weights get too non-uniform, then you're not going to use it, and you're going to. But it's not a perfect strategy. I mean, it's one thing to do it, but even if everything is perfectly Gaussian, you wouldn't extract from that saying, actually, I should use a Gaussian. You would still use a particle filter somehow, even though you should be. So it's not perfect. So that's an open question. How to choose these bridging parameters in practice. Adaptively. I mean, of course, you can fix it and try and test if you, but that's not perfect, right? So adaptivity is still an open question, but it's certainly something that's available now. It's becoming available. Okay, so in terms of these transformation matrices, it's basically all I'm saying is you compute one set of these transformation matrices, you get another set of these transformation matrices corresponding to different methods, and then if you multiply it out, you get yet another of these linear transformations. So it's a zoo now, essentially. I mean, or well, zoo is not, it sounds a bit negative, but you have many options. Let's put it this way. And here again, this is the big open question. I mean, how you use this in practice, and also in terms of practicality, given a certain ensemble size, will the alpha actually go away? Let's say if 0 is the ENKF for simplicity, will there be a significant non-zero? And Kuensch again with the Swiss method has found that they applied this to convective, high resolution forecasts. They found that the parameter indeed, I mean, it really helps to bring in part of the ensemble Kalman filter. So use this mixture instead of just a single Gaussian, and it's also better than using Dirac deltas. Okay. So here, this is, again, the Lorentz 63. So this is a bridging parameter. This is the ENKF. So you see, basically, the ENKF is fairly insensitive to the number of particles at that stage in this size. A particle filter is here. So with just 15 members, the particle filter is simply not working. If you have 20, then you get roughly the same quality as the ENKF. If you increase the number of particles, you go below in this particular setting. And then in between, if you choose a bridging parameter, of course, here you can read off the optimal value, which is here half. And as you have more and more particles, you see what you expect, that ultimately alpha will become 1. You use a particle filter because that's the optimal choice. But that requires a large number of particles. So in practice, you probably like here. But even here, so the particle itself is completely divergent. But you can mix in a little bit of a particle filter and easily improve the ENKF. That's for Lorentz 96. Anyway, let's finish off. with another research direction that I'm not so actively involved, but that's something Peter Jan van Leeuwen is, for example, promoting, and Alexander Chorin from Berkeley is saying, okay, going back to this control idea that I mentioned earlier. They're saying basically, if you have model errors, you can modify your model to a certain degree, and if you do it well, then these modifications or control terms guide you to the regions where the observations are. And it's kind of intriguing because it sort of combines nudging in a way. So you can use nudging as a heuristic to get such control laws. And of course, nudging, then you have to compensate by saying, okay, I changed the dynamics, so I have to compute the associate radon-Nikodym derivative, but I can't do this. I gave you the formula this morning. So you give me a control law that you use to change your dynamics, and I can tell you how you should compensate for when you then do the inference step using this formula, which was an integral along U in your assimilation step. So if you do this well, then that will exactly compensate the change of measure you get from the data. So there are compensating effects, all right? You make one error, and that error or change is exactly the change that you need to be in the right spot. So typically, so there's basically the industry is, or the challenge is to a cheap way of finding steering mechanisms. But it requires that, of course, you accept model errors, because if you don't have a model error, there's no freedom for you to steer stuff around. I mean, you can still, of course, do nudging, but then it becomes really just a heuristic tool. I mean, as far as I'm aware, there's no mathematics behind it anymore. It's just, I mean, I wouldn't know how to change how to write down this as a change of measure that you can then use further. And so this is the idea. You have your original model, and you add such a term in whatever way you prefer, and that gives you a new proposal step, essentially, a new proposal density. And so this is a bit dense, this transparency, but again, the best way to understand these techniques to always go to the joint distribution first. So this is a joint distribution of the data, the forecast, and the analysis. These are the players, right? Data, forecast, analysis. And you write it down as a joint. So this is the likelihood. This is yn conditioned on xf. This is the model forecast. So this is the transition kernel from the analysis to the forecast. And this is the distribution of the analysis. And that gives you the joint distribution according to the laws of conditional probability. And now you can swap orders here. I mean, this is the game you always play. So you can say, well, this is the same as this we keep the same. Then this is the likelihood given the analysis. So the original likelihood is the one. Sorry. This is okay. The analysis is the old thing in this context. So this is the last from the last step. That was analysis, and then the forecast is now what you're forecasting, and then this is the likelihood of the forecast, right? So this analysis is not to be confused with what you want to compute. So this is analysis from the last step, right? So you take the analysis, turn it into a forecast, turn the forecast into analysis. But here the analysis is the last analysis, and you propagate this forward to give you a forecast. And so you can mathematically just write it like this. So there's an equivalent formula, just switching orders of, as you do in base formula, I mean, that you can reorder things. Now the proposal density is the one where you change a u. So u here is 0. This is original dynamics. And so here you plug in some u. So this is this is the proposal step. And then you have to take the ratio. So again, it's radon-Nikodym derivative, but it's just, because everything is a density here, you just take the ratio of the two. And this gives you the weighting. So in a perfect scenario, this would be the same as up here, and then all particles have the same weight. Now this is a bit difficult, but what you can do, I mean, this term is here the same, so this is the same as here. So this drops out, so you're left with this. And so then using this equality, you basically get this. Now, the best thing you can do is to find the use that matches exactly this. So this is the forecast distribution given the analysis and the data already. So this is a look ahead way of doing it. So when you're already doing a forecast, you're already taking into account that you're observing something in anticipation of it. And so then this term drops out, and you're left with this. And these weights are typically, the difference in the weights are then smaller because you basically already used the data in a look-ahead way.